I've been reviewing a lot of multimeters over the past few months. The meters that I've reviewed range from a few dollars to a few $100s. It's astounding to me that there can be so many different multimeters on the market. At a superficial level, they all do pretty much the same thing. After evaluating more than 2 dozen of them, I've learned a lot. I decided to make this video to share the things that I have learned over the course of these reviews. Multimeters these days tend to be loaded with features. In this video, I focus on the features that have stood out, those that have helped separate a good meter from a great meter. Every manufacturer has a different approach to bringing a product to market. As a result, there are idiosyncrasies in the realization of features that are not readily apparent from a feature checklist. This is one of the reasons I perform my reviews, to show most functions and demonstrate exactly what you will encounter in actual use. If you found this video to be helpful, please give it a thumbs up and subscribe to my channel. I welcome your feedback as it helps me to know where to focus my activity. Please let me know if you feel that there are important features that I've missed. If you've been following my channel, I hope you feel that my multimeter reviews have improved over time. I also hope you find this information helpful in selecting your first, or perhaps your 50th multimeter. Now, let's get into the features. Multimeters started out as devices with a needle and a gauge that relied directly upon electrical current flowing through a coil to move the needle and produce a reading. The physical coil has a limited absolute range of movement and thus measurement. With the wide dynamic range of values to measure, it is necessary to introduce circuitry to bring the values of interest into the range of the sensor. For example, when measuring small voltages, resolution may be down to the millivolt, whereas when measuring high voltages, the resolution may only be in volts or tenths of a volt. The division into ranges is still relevant with digital multimeters and their sensors. Auto-ranging, where the multimeter goes through its ranges and automatically settles upon the correct one, becomes feasible. I don't bother with manual ranging multimeters as there is little benefit and less convenience in using them. Auto-ranging is fast and does not appear to raise the cost of the meter. One would think that if auto-ranging is good, then auto mode detection would be even better. I find this not to be the case. Auto mode detection is actually a mode unto itself. In this mode, the meter can test for AC and DC voltage, resistance, and sometimes diode. If the resistance is low enough, it produces the same tone as continuity mode. The deficiency of this approach is that it requires the meter to run through a sampling process that alternates between sensing for external voltage and resistance. This reduces performance and limits the ability to measure small voltages. The most notable impact is on continuity, as it can take a second or two for the meter to conclude that it is sensing a low resistance and activate the tone. I'm generally not fond of auto mode. However, some meters allow for manual override in order to address the shortcomings that I mentioned. There are a variety of devices that put out a signal with varying frequency. Multimeters have expanded beyond the basics of voltage, resistance, and current to include the ability to measure a wide variety of electrical properties. One of the trickier ones appears to be frequency and duty cycle. This was not a capability that I paid much attention to early on. However, since getting my LB02A process calibrator, I have been testing it. Many multimeters that claim to support frequency measurement are unable to detect and measure the square wave signal produced by the calibrator. Square wave signals are often used for communication between devices in industrial control systems, and these meters are usually capable of measuring the sinusoidal signal of AC power systems. So for example, we'll plug in this ZT111. You can see it's showing 100 Hertz and a 50% duty cycle, pretty close. Now if we come over here to the 58C, that's plugged in, and we got nothing. One of the most common uses for a multimeter is to detect if 2 points are electrically connected. Electrically connected is usually defined as a resistance of less than 50 ohms between those 2 points. When the points are connected, a tone is emitted. The reason for a tone is that it allows the user to concentrate on getting the probe tips in the right place rather than looking at the display. For each meter that I test, I assess how quickly the meter responds with a tone when the probes are tapped together. Some people think that probe tapping is a silly way to test continuity, but it seems that this is the method employed by almost all reviewers. Rapid response means that when testing a circuit, poor or intermittent contact between the probes and test points will still produce a tone. Poor responsiveness means that weak connections may not trigger the tone, resulting in some frustrating troubleshooting sessions.
Overrange. Overrange.
Probes, also known as test leads, are an accessory that is included with almost every multimeter. Good probes can make a meter a joy to use. Bad probes can cause immense frustration. In general, top-tier probes will use wires with silicone insulation due to their superior flexibility and to avoid getting inadvertently melted on a busy workbench. Probably more important is gold plating on the tips. Gold plating, if you can see that, resists surface oxidation and thus makes better electrical contact. Manufacturers select the quality of probes included in the package, and so this can be an important consideration when selecting a multimeter. And then these are PVC probes. And you can see that the cables are not very flexible. They kind of have a mind of their own, and the tips are fairly dull, probably nickel plated, and it tends to cause oxidation, and they don't respond as well. Most multimeters include a diode check feature as part of their basic feature set. Diodes are very basic semiconductors that allow electricity to flow in one direction only. Properly operating diodes produce a voltage drop when forward biased. When reverse biased, there is no current flow. The size of the voltage drop is based upon the diode construction. Generally speaking, the voltage drop is between 0.2 and 0.8 volts. Light-emitting diodes produce a voltage drop between 1.5 volts and 3 volts. Diodes can fail open, meaning they no longer conduct electricity when forward biased, or they can fail closed, meaning that they freely conduct electricity in both directions and act as a short circuit. As you would guess from its name, Diode Check is intended to help test diodes, both regular diodes and light-emitting diodes, for proper operation. In this mode, the multimeter emits a small voltage and detects the voltage drop produced by the diode. For regular diodes, some multimeters will produce an audible signal when a valid forward bias voltage is measured. The audible signal, usually a quick beep, is very helpful as it allows you to stay focused on the components being tested. You don't need to glance at the multimeter while making sure that the probes are still where you intended them to be. For LEDs, diode check can be used to determine if the LED is operating by lighting the diode. LEDs of different colors require different voltages in order to light. Some multimeters can light all diodes, while others do not emit enough voltage to light the blue and clear LEDs that require more than 2 volts to light up. One of the big no-nos when making measurements is to attempt a voltage measurement with the test leads connected to the current socket. This all has to do with how the measurement circuitry in the multimeter is configured. The first thing to note is that voltage and current measurements are taken when a circuit is energized. All the other measurements are taken when components are removed from a circuit or the circuit is not energized. Current measurements are performed by placing an internal component called a shunt resistor with a very low and calibrated resistance in series with the circuit being measured. The voltage drop across the shunt resistor is measured and the current is calculated using Ohm's law using the known value of the shunt resistor. Using Kirchhoff's law, we know that the current is equal in all portions of a series circuit, and thus the current of the circuit we are measuring is equal to the current at the shunt resistor. Voltage measurements are taken by placing the meter measurement circuitry with a high known resistance in parallel to the portion of the circuit being measured. A high resistance is used so as to have a minimal impact on the circuit being measured. In this case, we measure the current flowing through the meter and use Ohm's law to calculate the voltage. Once again, Kirchhoff's laws, the voltage is equal in parallel branches of a circuit, and thus the voltage of the circuit we are measuring is the same as the voltage in the meter. Now, when we attempt to measure voltage using the current measurement pathway in the multimeter, we are placing the shunt resistor in parallel to the circuit we are measuring. Because the shunt resistor has a very low resistance, close to that of a pure short circuit, almost all the current that can be provided by the circuit at that point will flow through the shunt. As you know, a short circuit causes the opportunity for a very high amount of current. In a meter with a fuse, the fuse will blow, thereby protecting the internal circuitry of the meter. If no fuse is present, the circuitry will be destroyed. The best choice is to prevent this situation from occurring in the first place. Different meters have taken different approaches to prevent this from happening. Some show a message on the display when you are changing modes to remind you to move the test leads. Unfortunately, the message is shown briefly and you may miss it. Others light up the sockets to tell you which ones to use in a given mode. However, the lights are only present for a few seconds, and once again, you may miss it. The best solution I have seen is a warning tone and error code when the leads are connected to the wrong socket. You can't miss it. You can't miss it. Despite the presence of electricity almost everywhere around us, electricity is dangerous. It does not take a lot of electricity to injure someone or damage electronics. Most battery-operated consumer electronics operate at a relatively low voltage like 5 volts or 12 volts that is not able to overcome the resistance of dry skin. Even at these low voltages, electronic circuits can be damaged if too much current flows through them. Higher voltages are found in the electrical wiring of most homes, with 120 volts being common in North America and 220 to 240 volts in Europe and Asia. These voltages are high enough to easily overcome skin resistance. Contact with these voltages would provide a significant shock or burn and can be lethal. Even higher voltages can be found in electrical distribution panels and industrial settings. The IEC has defined 4 safety categories for electrical test equipment. Cat 1 is the lowest category and refers to most electronic devices. Cat 2 is the most common household rating and would apply to most of the electrical outlets in a home. Cat 3 would be the environment of an electrical distribution panel, and Cat 4 refers to connections to the main electric utility and outdoor connections. When assessing safety, we need to consider safety to people and safety to our electronic test device. Protection mechanisms within multimeters come in many forms. There are electrical safety components like fuses, positive temperature coefficient thermistors, or PTCs, down here, and metal oxide varistors like MOVs, here. Fuses will blow if current goes too high and can handle high voltages. PTCs are considered resettable fuses and will inhibit electrical flow if current goes too high. However, they are usually limited to about 60 volts. And then MOVs will absorb transient voltage spikes that can damage sensitive electronics. And we can also see in the design of this multimeter, there are physical barriers that separate certain parts of the input pathway in case things can go really wrong. For higher energy environments, we also see several physical safety mechanisms. This includes the gauge of the wire that's used for test leads and insulating covers or shrouds that are placed over the exposed metal. At higher voltages, electricity will travel across small air gaps between two conductors. This is called arcing and is very dangerous. These covers are meant to reduce the amount of exposed metal in order to prevent arcing. And we can see this lead. You can see that. That's rated at Cat 2 without the shroud. And if we put this shroud on, now, if you can see that, that's rated for Cat 4 with that little tiny bit of exposed metal at the tip. Accuracy refers to how closely a measured value corresponds to the true value. Accuracy is an interesting consideration. With a few exceptions, almost every multimeter I have tested has decent accuracy. Every multimeter has accuracy specifications provided by the manufacturer. Most of the time, the meters are within the manufacturer's specification. It does not have to cost a lot to get a multimeter with good accuracy. While cheaper meters tend to have wider published tolerances, there are a few that perform much better than their specifications. I have tested a few meters that are less than $10 that have very good accuracy. These are without a doubt better than the first meter I bought from Radio Shack for over $100 when I was starting out in the hobby. Accuracy has only a small influence on the price of a multimeter. Accuracy is usually specified as plus or minus a percentage of the true value plus some number of counts, where counts is the amount of variance in the least significant or rightmost digit shown on the display. An element of frequent confusion is the difference between precision and accuracy. As I stated earlier, accuracy refers to how close a measurement is to the true value. Precision, on the other hand, refers to how closely repeated measurements of the same input are to each other. We expect that when manufacturers provide specifications, they are indicating how well the meter is at measuring the true value. While we can't assess the true accuracy of a meter without comparing to a known reference, we expect that the meter was calibrated during the manufacturing process. A meter that produces highly consistent measurements that are a long way from the true value would be of little use to us. Some meters are meant to be carried to work sites, which can be a rough and tumble sort of environment. Other meters are meant to stay in the relative safety of a workbench in the lab. Meters that are used at work sites need physical durability. Meters are jostled about, they're dropped. And the expectation for tools in this environment is they can withstand this sort of abuse and keep on operating reliably. This is why most handheld meters have large rubber overmolds. These are meant to protect the unit and absorb the shock from drops. At the high end, the overmolds are like protective cocoons. At the low end, these are more decorative than protective. There's a definite price premium for meters that can withstand being frequently knocked about while continuing to operate both reliably and safely. Resolution refers to the smallest difference in value that the meter can detect and display. Resolution is commonly specified in one of two ways: counts and digits. Digits is the older approach, where resolution is stated in terms of number of full significant digits along with a half digit. A full significant digit can show a value from 0 to 9, while the half digit can only show the value of 0 or 1. The half digit is the leftmost digit on the display. Yes, it's a little odd, but that's the approach that many manufacturers took when digital multimeters were first introduced. A basic multimeter would be 3.5 digits. That's a 0 or 1 in the first position, with 0 to 9 in the other three positions. In other words, the full range runs from 0 to 1999. As the technology evolved with better analog to digital conversion, full-scale ranges could be expanded with ranges from 3,999 and 5,999 being common. The fractional digit terminology doesn't work well with these expanded ranges because of the unfortunate use of 1/2 to describe the leading 0 and 1. It probably should have been called 1/5 of a digit, but that doesn't sound so good. Counts was introduced as newer terminology to describe the number of values in the full scale. Thus, 3.5 digits is 2,000 counts, a range that runs to 3,999 is 4,000 counts, 5,999 is 6,000 counts. The oddity in naming has a small twist at the edge where 4 full digits are used. These are referred to as 9,999 count meters rather than 10,000 count meters. I suspect this is because consumers might expect to see 5 digits in 10,000 count meters instead of 4. Benchtop multimeters continue to be marketed in terms of digits, while handheld units, like this Unity, are specified in terms of counts. We can see the 22,000 counts shown here. Another odd aspect that can sometimes be seen is the slight allowance for the meter to exceed the stated count limit before switching into the next higher range. This is because the analog to digital conversion range in binary is slightly wider than the decimal range we see displayed. For example, in the full range of an 11-bit analog to digital conversion, we have 2,048 possible values, slightly more than the 2,000 counts we require. Here's an example of a multimeter going slightly beyond its specified counts. This Zoyi ZT100 is a 4,000 count multimeter. The highest value it should show in the current range is 3.999. The calibrator is set to 3.99 volts, and we are seeing 3.993 on the meter. When I change the calibrator over to 4.05 volts, I should lose a digit, but I don't, and you can see the reading at 4.052. Now, if I push the voltage up to 4.1 volts, the meter finally goes into the next range and a digit is removed, and so I only see port 4.09. Resolution is the most significant factor that influences the price of a multimeter. The cheapest multimeters have a solid 2 to 3 digits of resolution and sell for under $10. As the number of digits of resolution increases, so does the price. 4 digits of resolution is about $100, 5 digits is about $500, and 6 digits will cost about $1,000. Beyond this, there are meters with 7, 8, and 9 digits of resolution, with exponential increases in price. I would argue that for most people and entry-level hobbyists, 3 digits of resolution is all that is required. It is greater than the manufacturing accuracy of most electronics components. The people that need more resolution are designers and technicians that need to detect small differences when implementing or troubleshooting a circuit. For the rest of us, a difference of a millivolt in a 5-volt circuit is usually not relevant. Before moving on, let's have a look at a few bench multimeters and their resolution. This is a Siglent SDM4065 multimeter with 6.5 digits of resolution. This is a Keithley DMM7510 multimeter with 7.5 digits of resolution. And finally, this is a Keysight 3458A multimeter with 8.5 digits of resolution. That takes us to the end of the list. If you think there are important features that I should have mentioned, please leave a note in the comment section below. If you found this video to be helpful, please give it a thumbs up and subscribe to the channel. Thanks for watching, and until next time.